So this is how you solve LeetCode 2858, which is minimum edge reversals, so every node is reachable. And this is a pretty good exercise for BFS, trees, and memoization. And while the difficulty is hard, I believe it would more fall under a medium category, so long as you understand a lot of the key fundamentals of graph theory. So some of the key points of this is that you have nodes from 0 to n minus 1, which means you have n nodes. You have a 2D array of edges where each represents a directed edge, which means it's a directed graph. And you're looking for edge reversals, which means a change in the direction of the graph. And then you have to find the minimum number of edge reversals to allow for one node to have access to the rest. So basically, the minimum number of edge reversals for each node to make that node the root of the graph. So and one other key thing is that this graph would form a tree if its edges were bidirectional, which is very useful to us. So I guess some of the key takeaways are that since you have nodes from 0 to n minus 1, you only need an array rather than a map or a dictionary. Since it's directed, it'll be useful for us to keep an in and out array, as you can see here, which represents all of the nodes that are pointing to a specific node and all the ones that are pointing out of a specific node. So here, for example, we have 1, which has 3 in its out array, and has 2 in its in array, since 2 is pointing to 1. Since it's a tree, that'll make the BFS significantly easier. And you won't need to keep a scene array, since you won't have any cycles. Yeah, I'd say that's a pretty good start. And the way to go about this problem is to iterate through every node, so from 0 to n, and maintain and keep a total for each node in a recursive solution. Now, how does this total change? When you come to any particular node, you can look at the in degree and the out degree. For the in degree, these are nodes that have to be reversed. So anytime you come across an in, you'd go to that node, you'd recurse into that node, and you would increment the total. And anytime you come to an out, you'd go to that node, and you wouldn't increment the total. So I guess we can run through an example here. You start at node 0, there aren't any outs, so you have to go to the in, which is 2, and you have to increment the total by 1. And then your recursive BFS goes to node 2. Keep track of 0 as the previous node. Do not go to this one when you're incrementing out. Instead, go to 1, since that's the only other node. And then from 1, do not go back to 2. Instead, go to 3, since that's the only other one out. And 3 has nothing left, so you return and get 1 for zeros. And I'm not sure if I mentioned it, but our answer will be an array. It'll be 0 to n, where each index I represents the number of reversals that are required to make the ith node into the root. So yeah, I'd say that's a pretty good start, and we can get into the code. So first thing, I suppose we can make the arrays for mapping our in and out degrees for each node. So that would look like a blank array for in range n, and then you can do the same thing for the outs. And then the next step, we could go about filling these two arrays with our edges. So for edge and edges, remember that edge 0 will be the node pointing to edge 1. So for outs, edge 0, we can append edge 1. And then for ins, edge 1, we would append edge 0. Now we can go about doing the breadth first search, but before that, we can iteratively call the breadth first search. So I suppose we can do r equals BFS I -1 for in range n, and I'll get into this BFS later, but then you turn r. So BFS will look like this. Since there is no previous, we can use -1 since we are confident that it won't be in our nodes, since our nodes are bounded by 0 to n. So that can't be, yeah, -1 can't be in our nodes. So we can iterate through all the nodes in the current nodes outs, which is all the nodes that the current node is pointing to, and increment. First we'd have to maintain a total and increment that total by BFS using the node now as our current and our current node as the previous. But an important thing is to check if node is previous, since we don't want to get into an infinite loop and we want to mark all previous nodes. In this case, we would continue. And now we would do something similar for node in ins pair. If node equals previous, except one little thing we can do here, +1, since each of the in nodes we would have to reverse, thereby incrementing our total by 1. And then, of course, at the end, you'd simply return the total. So the solution works. It might not get accepted because of its poor runtime, but with enough time, the solution works. But it's inefficient, and we can see that because why are you recalculating the total or rerunning the BFS for an instance that you've already encountered? And what I'm getting at here is that you can memoize certain relationships or certain edges in the graph so as not to do the same work over and over. So I'll show you how that's done. First, we can create a memo, which will be a map. And right here, after checking this, we can check if, yeah, so in this memo, we will store the current node and the node it's pointing to as a tuple. And then check if that's in memo, or if it's not in memo, then we would set memo of cur node. Sorry, like I was saying, we would allocate this BFS return value into the memoization map, and after that we would just increment total by this value. We can do the same exact thing here, except obviously right here we'd have to increment this by 1 to account for, obviously, since we have to reverse the edge. And yeah, this is how you can use memoization and BFS to complete this LeetCode problem.